Let's study alternative and probably more convenient ways of writing the transfer function of a system. So imagine we're given a transfer function in the shape we know so far, the one which is derived from the differential equation describing a system, and we calculate its poles and its zeros. Remember, the zeros are the values of s, which make the numerator equal to 0, and the poles are the values of s, which make the numerator, the denominator equal to 0. So we calculate all of them either by hand if the orders are not very high, or applying some numerical method, and then we can rewrite the equation in the following way. Well, not the equation, but the transfer function in the following way: s plus z1 times s plus z2 times all the rest of binomials until the s plus zm, because there have to be s poles, since the order here is s. Sorry, m poles, because the order here is m. And in the denominator we would get s plus p1 times s plus p2 times all the rest of poles, all the rest of binomials, times s plus p, in this case n, because n is the order of the denominator. We can at the same time we can draw the poles and the zeros in the complex diagram. So for example, this is the complex plane. So for example, let's imagine z1 is a real pole. Well, is a real zero. Well, we can draw it here, and we indicate the position of a zero with an O. So here I write minus z1. But hold on, why minus z1? Why not just z1? Well, because the pole, sorry, again, the zero is at minus z1. And why is that? Well, because if we replace s by minus z1, we would get minus z1 plus z1, and this is equal to 0, and then the whole numerator is 0. Okay, if we have, for example, complex conjugates, remember that the roots of a polynomial can be either real numbers or complex conjugate pairs. Well, if it turns out that these two poles are complex conjugate numbers, then we can find them here. This would be minus p1, and this one is minus p2, and as you see, the poles are indicated with an x, and since those two are complex conjugates, minus p1 is the same thing as minus p2 bar, the complex conjugate of minus p2. And we could do the same with all the rest of poles and zeros. But these two ways of writing the transfer function have a drawback in common, and that is that the gain of the system is not apparent. It's not we cannot get it directly from the expressions. We have to calculate it. The gain of a system, or the static gain, is just the value of the function when s is equal to 0. Well, in this case, g of 0 is b0 over a0, because all the rest of terms are 0. And in the second way of writing the transfer function, the gain would be z1 times z2 times all the rest of z until m over p1, p2, and all the rest until pn. Well, in either case, it is not very handy, I guess. So maybe a better way, well, in my opinion, definitely a better way to write the transfer function would be the following one: g of s is sum k times s over z1 plus 1 times s over z2 plus 1, and one of these terms for each 0, s over zm plus 1, and the same with the denominator, s over p1 plus 1, s over p2 plus 1, and s over pn plus 1. What value is this k? Well, obviously this is k, this value is k, the static gain of the system. But now we have it directly in the expression. We don't need to do any operations to calculate it, because all the rest of terms, each one of these terms here, each one of them have what we call unit gain. But the positions are of the poles and the zeros remain the same. For example, in this one here, again, minus z1 over z1 plus 1 is just minus 1 plus 1, and that is 0. Okay, there's an exception to this, which takes place when for example a0 here is equal to 0. In that case, we have a pole at the origin of the plane right here, and we call that pole, as you'll see, an integrator. Well, in that case, this p1 maybe could be removed. Well, I leave the p1, but I'll put here an s, and then this pole here would be the pole number n minus 1. So there are n minus 1 poles plus an integrator, which is just a pole at the origin. Well, in that case, the gain of the system is not k, but k over s. That is k over 0. So the gain is the static gain is infinity. But nevertheless, we still prefer this way of writing the equation, because all the terms but the integrators have still a unit gain. If there are more than one integrator, then we can put it here an exponent n, capital N, which is the number of integrators. Well, there are some cases, some strange cases, in which n would be negative, and then what we would have here instead of a pole is a 0, but that doesn't, maybe 1 0 or more than 1 0, but that doesn't happen very often. Okay, so this is the most general expression so far. Nevertheless, we don't like, if we have complex conjugate poles of zeros, we would have to write them down, to write them in the denominators of these terms, and we don't like the imaginary unit to be included in transfer functions. So we have to change somehow or make the expression more general to include the case of complex conjugates. So let's think of a system with only two poles, which are complex conjugates, S over P plus 1 and S over P bar plus 1. The poles are here, for example, here. Okay. Well, if we multiply this expression by P and P bar, we get P times P bar over S plus P times S plus P bar. But this is just the expression for the module of a complex number. This is just the module of certain complex number. Well, this is actually just P. So this is the module of P, and in the diagram, this is this distance here, which we denote by omega n. So sorry, this is P times P bar is the module of the number squared, and that's why this is equal to omega n squared. Okay. If we do the operations in the denominator, we have S squared plus P plus P bar S plus P times P bar. Okay, and we've just seen that this is equal to omega n squared. Alright, in the case of this term, well, if we call the real part of P, this is minus P. Well, if its real part is sigma, so this is minus sigma, and its imaginary part is omega d, here we have sigma plus omega d plus sigma minus omega d. That is 2 sigma, 2 times this segment here. But this segment is simply sigma is just omega n, the module of P, times the cosine of this angle here, the cosine of theta, the cosine of theta. And we call omega n, we call it the natural frequency of the poles, the natural frequency. And the cosine of theta of z I don't know how to pronounce it. The cosine of theta is called the Greek letter zeta. The cosine of theta is zeta, and this is also called the damping factor, or just the damping. So with all that, this can be written as omega n squared over s squared plus 2 times the damping factor times omega n times s plus again omega n squared. And as you see, this has unit gain as well. Some people prefer to write it this way. This is s squared over omega n squared plus 2 times zeta times s over omega n plus 1. But in either case we have a unit gain. So once we've developed this, we can write the most general way and the what we will call the standard form of writing the transfer function of a system. Let me write it. Here it is. The standard expression of a transfer function has here the gain, the static gain, unless there are some integrators or derivators. If capital N is minus 1, so then this would be the gain. And here the product of all the real zeros of the system. Here the product of all the terms corresponding to all the complex zeros of the system, the terms corresponding to all the real poles of the system, and the term corresponding to all the complex conjugate poles of the system. So it is very important that you learn how to go from this expression to this one, especially when we get to the frequency domain.